Oxidation-reduction reactions are also called redox reactions because that's a lot shorter. In these reactions, we have electrons being transferred from one reactant to the other. So something's losing electrons, something is gaining electrons. Many of these involve something reacting with oxygen. And I think that's where the oxidation name came from. So iron reacting with oxygen to form Fe2O3, iron 3 oxide. This is an oxidation reaction. If there's an oxidation, there has to be a reduction also. Here we've got C8H18. The carbon is reacting with oxygen to form CO2. It's being oxidized. Here we've got water reacting with oxygen. It's being oxidized. Here's an example. This balloon contains a mixture of hydrogen and oxygen gases, very flammable. So you touch a candle to that and it goes kaboom, and the ceiling tiles bump up and your ears ring for a while, and it forms water. That's an oxidation-reduction reaction. So all combustion reactions are redox reactions, something reacting with oxygen. You can also have redox without combustion. So here we've got a metal and a nonmetal reacting. We've got sodium and chlorine reacting to form sodium chloride. What's happening here is the sodium ion is losing an electron to become a sodium ion, and the chlorine atom is gaining an electron to become a chloride ion. So we've got loss of electron and gain of electron. So here we have sodium reacting with oxygen. We just learned that that would be a redox reaction, something reacting with oxygen. Here we have sodium reacting with chlorine. That's also a redox reaction. So a metal reacting with a nonmetal element, those are going to be redox reactions. These are relatively easy to identify because here we've got atoms and here we have ions. So a sodium atom becomes a sodium ion. Sodium atom becomes a sodium ion. This oxygen, the oxygen atom in that molecule becomes an oxide ion, and the chlorine becomes a chloride ion. When you look at these formulas, you kind of get an idea of why we don't write all the charges in formulas for compounds. It gets really messy and ugly. So to make a free element into an ion, you have to either gain or lose electrons. And if one atom loses an electron, something else must accept them. If something gains an electron, it has to come from somewhere. There's no homeless shelter for electrons where you can take them when you don't want them and just go adopt them when you do. You have to get it directly from another atom or ion. So we always have oxidation and reduction together. So in our sodium chloride example, the sodium is losing an electron. That's oxidation. Oxidation is loss of electrons. The chlorine is gaining an electron. That's a reduction. Reduction is gain of electrons. And a good way to remember that is oil rig. Oxidation is loss. Reduction is gain when we're talking about electrons. So when we've got ions being formed, we can look and say, oh, well, that became a positive ion. It must have lost an electron. Oxidation is loss of electrons. That was oxidized. I actually think through that whole thing because I don't use this often enough for it to just become pat. I have to think through it every single time. It's tedious, but I get the correct answer. What if the transfer is not complete? So if we have hydrogen and chlorine reacting with each other, hydrogen molecule, that electron density is shared equally. Think of that as the blanket, and these two hydrogen atoms are sleeping in a bed. Here we have chlorine, two chlorine atoms. They are identical to each other. They're going to share their electron density or their blanket equally. When we mix it up and put hydrogen and chlorine in the bed to sleep together, chlorine is got a stronger pull on the blanket, and so hogs the blanket, hogs the electron density. This is not an ionic compound, but we have an imbalance here. Chlorine has gained electron density, hydrogen has lost electron density. So there is oxidation and reduction. It's just not a complete transfer. So those are harder to identify because you don't have the ion charges to help you out. So we use something called oxidation states to identify what's going on, who's gaining or losing electron density. And this is just a made-up thing that we use to keep track of it. So oxidation states are not ion charges. They are imaginary charges that are assigned based on a set of rules. Ion charges are real and measurable. Oxidation states are not. Oftentimes an oxidation state is the same as the charge, and so that's why it can sometimes be confusing. They're not exactly the same thing. So the rules, as with many sets of rules, when you write them all out, they look a little more confusing than when you actually get used to them. It's like learning to play a new board game. You go through the rules and you're like, oh my goodness, I'm never going to get this. But you play for a while and then it becomes simple and you remember it. So bear with me. Here are the rules. Free elements have an oxidation state of 0. Monoatomic ions have an oxidation state equal to their charge. The sum of oxidation states in a compound is 0. In a neutral molecule, the sum of the oxidation states is 0. In a polyatomic ion, the sum of the oxidation states is equal to the charge on the ion. So all of those rules, we can think of oxidation states as being just like ion charges. In an ionic compound, the ion charges have to add up to 0 for the compound, right? In their compounds, metals have positive oxidation states. They're always going to have positive charges. Group 1 metals are always +1. Group 2 metals are always +2, just like their charges. What's a little different is when we get to the nonmetals. So we have a set of rules here, and the rules go in order. The way I think of this is the nonmetals would like to have an oxidation state equal to the charge they would have if they were an ion. So fluorine, when it's an ion, is a fluoride ion, a -1 charge. Hydrogen is a +1 charge. Oxygen has a -2 charge. The group 7 elements, -1. The group 6, -2. The group 5, -3. So all of these nonmetals are saying, hey, I want the charge, I want my ion charge. They don't get a charge, but they get an oxidation state like that. Well, they can't all have what they want. And so we have a list of priorities. And fluorine gets first choice, then hydrogen, then oxygen, then 7, 6, and 5 by groups. So how do you remember that? What's that? Pho. Yummy noodles? Anybody? Come on, you guys eat pho, don't you? Yeah, it's good stuff. Okay, it's going to help us remember. So if I take that and I just get rid of a smidge of the P, now it's an F, and you could still pronounce that pho, right? And then I've got 7, 6, and that's actually a restaurant around here, pho 7, 6, and you put a 5 on there. Pho 7, 6, 5. So that's the order. Fluorine, hydrogen, oxygen, 7, 6, 5. I don't know, it works for me. We can have fractional oxidation states. We don't see them very often, but it's possible. Just so you don't get confused by why I'm putting my pluses and minuses where I am, the sign is written before the number for oxidation states and after the number for ionic charges. I will not try to trick you with that one. Let's practice. Assign oxidation states. You assign an oxidation state to each atom. Each atom has its own oxidation state. Well, in the first one, there's only one atom. It's chromium atom. What's its oxidation state? What's its charge? Does it have a charge here? No. It doesn't have a charge. It's written as an atom, right? So its oxidation state is the same as its charge, which is 0. Here we have same element, but chromium with a 3+ charge. This is a chromium ion. What's its oxidation state? 3. +3. It's the same as its charge. Here we've got CCl4. So these are both nonmetals. It's a molecular compound. So we can't look at ion charges because there aren't any ion charges. And how do we decide who has to be the bad guy, the positive one, and who gets to be the negative one? Fa765. So Fa765, fluorine, no fluorines. Hydrogens, nope. Oxygens, nope. Group 7, chlorines in group 7. Chlorine gets to choose its oxidation state. It will choose an oxidation state equal to the charge on its ion. 1 negative. Yeah. So chlorine will choose a -1 oxidation state. Carbon has to be whatever is necessary so that all the oxidation states add up to the overall charge on this thing, which is 0. So I have 4 chlorines, right? There's a chlorine, there's a chlorine, there's a chlorine, there's a chlorine. They each have an oxidation state of -1. So together, that's -4. What does carbon need to be if all these oxidation states are going to add to 0? It's got to be +4. So carbon has a +4 oxidation state. So figuring out what the carbon is, this is the same process we did with ionic compounds. Any questions about that one? SrBr2. Well, is this an ionic compound? Yeah, so let's look at the ion charges. So what's the charge on a strontium ion? +2. So the strontium is +2, and the bromide in that compound is what? -1. I'll get rid of this. So if you have monatomic ions, the charge and the ionic, the charge and the oxidation state are the same. Here we've got sulfur trioxide. Yeah.
For D, you said the charge and the oxidation state are the same, but together they're balanced.
Right. So the charges in an ionic compound add up to 0, and the oxidation states in any compound have to add up to 0. So I've got 2 bromines, they're each -1 and a +2. So this is sulfur trioxide, this is not sulfite ion, because there's no charge written. So 2 nonmetals, I use Fa765. There's no fluorine, there's no hydrogen, but there's oxygen. Oxygen gets to choose. What does oxygen choose? 2 negative. If oxygen was an ion, it would be a 2- ion, and so it will choose to have that as its oxidation state. Of course, I'm personifying the atoms. They don't actually choose anything. So if I have 3 oxygens and they're each -2, what does the sulfur have to be? 6. So the sulfur is going to be +6. Now, do you think sulfur's real happy about that? Probably not. Because sulfur is in the same group as oxygen, right? And so would probably prefer to be -2, but it's +6. Okay, last one, nitrate ion. So here we have overall a -1 charge. So that means the oxidation states have to add up to -1. But we're still going to go Fa765, and we'll see that oxygen gets to choose first. So oxygen chooses to be -2. There are 3 oxygens. They are each -2. And then we have whatever the oxidation state is for the nitrogen, and that has to add up to -1 because the charge on this polyatomic ion is -1. So the nitrogen is +5. Any questions? The math here is very simple, but you kind of have to mess around and wrestle with it until you see it.